Hello everyone of Gauss law and applications of Gauss law. Myself Dr. Sohail Rana, and we are studying electromagnetic fields and transmission lines. In previous two parts we have discussed various applications of Gauss law and their derivations. Today we will see the next type of derivation relation for Gauss law, which we later connect with the electric field intensity. Here we will study the application of Gauss law in the case of a sheet of conductor or a surface charge density, and its relevance with that we will discuss. Now let us consider this setup. This diagram we will consider for our discussion in 3D. Now here we can see we have one plane sheet. This plane sheet is filled with equal charge distribution. Say Q is there. This is filled with the charges. All over the sheet there are equal distribution of charges. Now this is our Gaussian surface in this case. What is Gaussian surface? Gaussian surface is the place where we can apply the Gauss law. So if we are able to apply the Gauss law, that surface we consider as the Gaussian surface. Now what we have to remember here? We have to remember that D are the force lines. These are invisible lines. They are not visible to our eyes. So they can enter from one surface and they can exit from another surface. So here we are considering that this sheet have the bottom surface and the top surface. So this is the top surface, and below that there is a bottom surface. So these arrows are representing the D lines, and these are the just reference for coordinate system. So here we can see in space we have one sheet, it has some thickness, and D is entering from the bottom plate and it is exiting from the top plate. So blur part you can see it's coming from bottom and exiting from top, and say this is normal to the surface of this sheet. That means it is making 90 degrees angle, right? So this is the setup what we have to imagine for this. Now as this is a sheet of charge, we have to consider the surface charge. We have to consider the surface charge density for our derivation. What are our routine steps? We consider that there is flux crossing through the medium and we are using the Gauss law. So say we have, what is D? D is the flux density. It is given by the cos per area. So what is cos here? Cos is maybe a charge or flux psi. Now in this case the area is surface area, not the volume. So here we have surface area. Now this is one type of density. Another type of density which is related to the sheet of charges. It is a sheet where charges are distributed. there we will have another density, that is rho s. Rho s is surface charge density. So this one is surface charge density, right? So this rho s is also same, it is given by cos per area. Now surface charge density, cos is same, that is the charge. So this is also equal to, say, q or q by s. So if we consider differential surface, for that we will get differential charge and differential surface. From Gauss law, if we want to keep, we can keep. So from here what we can say? We can say from this, we can say dq is equal to, this term will go to LHS. So it can become rho s ds. So from that, what will be the normal q? If you want to find out the overall q, for this we can take integration of right hand side, we will get rho s ds. So now if we consider the overall surface, or in other words, what we can say, we have psi is equal to q is equal to rho s ds, right? So rho s ds is nothing but, if we closely observe this, this is nothing but d bar dot ds bar. So it's another form of, say, d bar dot ds bar. So if you can equate, here d is nothing but same amount of charge enclosed can go out. So this is quite similar to the another point form, say, that is del dot d is equal to rho v. Del dot d is nothing but the divergence. If you remember, the divergence of d going in all direction will be nothing but equal to the volume charge density enclosed in that volume. That means if we blast this volume filled with charges, so the flux crossing across this flux density will be equal to rho v. Here also we are relating it with another term, that is charge is equal to flux. So there is very narrow difference between flux, charge and d and e. So let us move ahead. So now what we can say, but we have two surfaces here. Two surfaces are, one will be bottom surface, another one will be the top surface. So for psi is equal to q is equal to rho s. Now ds we have to consider 2. So two surfaces we can consider, one top, one bottom, and same we can also write in other terms as d to s. So if we equate these two terms, what we can say, rho s 2s is equal to d to s. So from here what we can say, d is equal to, d will be equal to rho s 2s divided by 2s. This term will go there. So this will get cancelled. This s will get cancelled with this s. So what we will get? We will get D is equal to, so D is equal to, we'll have say rho s by 2. In terms of E, we can write it as D is equal to epsilon E, or we can say E is equal to rho s by 2 epsilon. So this will be the case for surface charge density. Now let us consider a volume charge density. For that we require the Gauss law. For Gauss law, we will take the example of say we'll consider example of balloon. Say we'll consider the balloon with water, its divergence we will see. So here we can see, suppose this is one simple example of divergence. We will see this one. Say we'll check another one. Say this slow motion. Let us see this. Now this one, like if water filled balloon is there, we can imagine that charge is filled inside. So if we puncture it, what will happen? The charges will diverge outside. So outflow of these forces will be considered as the divergence. All the forces of water will blast outside, go outside, and the volume of the balloon will go towards 0. So that is something which is divergence. So for divergence, what we can say that the divergence is given by del dot. So del dot, we can say for this expression is del dot D, that is divergence of force lines going out. How much it will go? How much amount is present inside the volume? Say rho v. The same amount will go out of the balloon. So say here you can see the various example. So if they blast outside, the amount will be same. How much amount of water is filled inside, same can go outside. So how much charge is filled inside, the same charge can go outside in the form of flux density. That is nothing but the Gauss law, and that's what we are studying in different forms. So now the same divergence concept we have to discuss now. So for this, we'll consider one cube from which all the sides there the flux will go outside. So suppose we have we'll consider one test. We'll consider one test volume. Okay, and for this there will be different sides. So we'll consider the blast. It's going from all the directions, front, back, right side, left side. So all these things we have to consider with del dot D. So what is del? Del is a vector spatial operator. So it is called as divergence. It is given by dou x ax cap plus dou y ay cap plus dou z az cap. Now what this D will be there. Now what is our basic expression? We have say Q. How much Q is present is nothing but D bar dot ds bar. Now what is the differential surface? Now in this case we are considering that the flux is going in all the direction. So we have so many differential surfaces. This is one ds, this is one ds, this is one ds, and so on. Hello. Hello. చెప్పండి.
ఇది రోడ్డు మీద వర్క్ జరుగుతుంది, మీది కారు బయట ఉంది, గబుక్కుని గీతలు పడతాయేమని చెప్పి కాల్ చేశాను మీకు.
ఒక
వర్క్ జరుగుతుంది ప్రజెంట్, మీరు లేరని చెప్పి మీకు కాల్ చేశాను.
ఒక 15 minutesలో వస్తున్నాను నేను.
ఓకే. కారు గబుక్కుని గీతలు పడతాయేమో.
ఓకే వస్తాను. సరే. Okay, so this we have to consider from all the directions. So there will be, say, top surface. Say we have to consider the top surface. For top surface, which constant plane is this? The top surface is z constant plane. So because if suppose here height is, say, from 0 to 5 meter, everywhere this height will be 5 meter. So for top surface we can write dsz. So this top surface dsz will be equal to product of other two, say dx dy. Then if we consider bottom surface, bottom is also z constant surface, but bottom one will be some opposite direction, but it will also have the same dx dy. We have discussed it in the Cartesian coordinate system in the beginning classes. Then if we consider the right side and left side, say this is right side, which constant plane is this? The side wall is y constant plane. So it will be, say, dsy for one will be for right side, another one will be for left side. So this will be product of other two terms like dx dz, dx dz, right? So similarly we will have the front side and back side. Front side is x constant plane, so it will be dsx equal to dy dz. Now what are all those things? These are all sides. We have to consider this ds is going from all the sides. So this we have to take into consideration all of them. So what we can write expression for this? Say we can write it as so total charge q will be equal to, first, say, d bar dot ds bar for top surface plus d bar dot ds bar for bottom surface. Then for left side, same term will get here, plus right plus front and plus back. So this charge enclosed in that q or rho v is addition of all the direction surfaces. So let us solve them one by one. So we will get So one by one we will take, say, for d bar dot ds bar equal to q for top surface. So for top surface this is dsz. dsz is dx dy. So we will keep that. So we can modify it. D bar for top is, say, d top dx dy. Direction will be in the z. This will be equal to charge q. Now d top means the flux density crossing the top surface. This can be given by some predefined function. This predefined function for that partial part will be given by, say, d top will be equal to dz plus dz by 2 into dou dz by dou z into dx dy into some direction az cap dot az cap. This term will become 1. So we will get the simplified portion for the top will be, say, q will be integration. For this simplified we will get dz plus dz by 2 dot dou dz by dou z into dx dy. Now this is for the top one. For bottom one we will get the same expression but with the minus sign. So what we can write for that? We can write, for if we take the addition of top and bottom, say top plus bottom, so that will be equal to dou dz by dou z into dx dy dz. But this is nothing but dv. So here we can simply write dou dz by dou z into dv. So this is combinedly for top and bottom. Now similarly we can get for right and left. Say for right plus left we can write. Now in the same term, right and left are which constant plane? The y constant plane. So here in place of z we can get dou dy by dou y into dv. Similarly we can get for the front and back. What will be for the front and back? For front plus back will be equal to dou dx by dou x into dv. Now what we have to do? Just we have to take addition of all these different surfaces. So let us do that. So if we combine that, we will get, so we will get q is equal to psi is equal to total d bar dot ds bar equal to dou dx by dou x plus dou dy by dou y plus dou d z by dou z into dv. But here what we have, this can be directly this term, partial term is nothing but the del operator. So what we can write there, in place of that we can write as, say, d bar dot ds bar is equal to del dot d. Total d is addition of dx plus dy plus dz. Now this is, from here what we can say, del dot d, and along with that we have this dv here, right? So from here what we can say, del dot d is equal to integral of d bar dot ds bar divided by dv. Now this is nothing but the outflow, and here this is volume which is going to 0, the blast of this del dot ds v dv and dv. So now this is nothing but, this overall is nothing but rho v, the volume charge density. So this one we can write as del dot d is equal to rho v. So here we have proved the divergence of electric flux density. So I hope this topic is clear. So next session will come with some new topic or examples. Till then, have a good day. Thank you.